In this video, we are going to observe the spanning tree protocol in operation. The spanning tree protocol is very useful in situations where you have multiple switches with redundant links. This is common in production switch networks and is done to provide fault tolerance. You can see here that we have two links going from S1 to S3, and so there is redundancy between switch 1 and switch 3. You can also have a situation where you have redundant paths. In this case, we have a path to PCC going from S1 to S3 to PCC. But we also have a path from S1 to S2 to S3 to PCC. One of the benefits of the spanning tree protocol is that it provides fault tolerance by recognizing when there are multiple paths through the network and controlling which paths are available by dynamically blocking and unblocking switch ports. And in the event that one of the switch ports was to fail, let's say that S3 has a failure on Fast Ethernet port 3. The spanning tree protocol will recognize the change and will make sure to unblock and forward packets on the path from Fast Ethernet 0/1 on S1 over to S2 and over to S3 and then finally on to PCC. Or, in the event that we have two switches, if port Fast Ethernet 4 was to go down on S3, it has the redundant link that it can use to forward packets in order to reach PCC. Let's look at another benefit of the spanning tree protocol. In this case, we have two switches and we have redundant links, so we have fault tolerance. If we turn off the spanning tree protocol, you can see here, no STP. The result will be a switching loop brought about by the multiple paths through the network, allowing packets to travel in a loop through the network. In this situation, Layer 2 broadcasts will multiply indefinitely and continue looping through the network until communication breaks down and becomes impossible. This is called a Layer 2 broadcast storm. With the spanning tree protocol operating and using the spanning tree algorithm, the spanning tree protocol will find the redundant links and block one of the switch ports, which enables a single path to the destination and thereby mitigates the possibility of a switching loop. So you can see in this scenario, on S3, port Fast Ethernet 3 has been put into a blocking state, and PCA is able to communicate with PCC. Let's see if we can observe the spanning tree protocol in action. I have a scenario similar to the one we've just discussed. I have switch S1 and switch S3, and I have redundant links between the two switches. I also have a PCA and a PCC. PCA has been given the IP address 192.168.1.1, and PCC has been given the IP address 192.168.1.3. We will observe the function of the spanning tree protocol as we initiate communication between PCA and PCC. Right now I'm working from PCA at 192.168.1.1 and I have a console connection to switch S1. Let's quickly verify that I can communicate with PCC. I'll type ping and the IP address, and you can see I receive replies. I'll open TeraTerm and we can go into our console connection into switch S1. The spanning tree protocol is enabled by default on 2960 Cisco switches. So to see information about the particular spanning tree instance that we're running, all I need to do is type show span, and then I'll press the tab key on the keyboard for command completion. And you can see the command is show spanning-tree. I'll press enter, and here is the basic information about this spanning tree instance for VLAN 1. We can see a lot of important information right here from the screen. First of all, this switch has bridge ID priority number 32769, which is made up of the bridge priority number 32768 plus the extended system ID, which is 1 because it's VLAN 1. The MAC address that this switch uses in the root bridge election process, hello times, and the status of the ports. We're also given information about the root bridge or the root switch in the spanning tree. Now we can see here and compare the information from the root bridge to this switch to see if this switch is in fact the root bridge. And when we do, we can see that the bridge priority numbers are the same. So we go down to the MAC address, and you can see here that this MAC address is lower 3D80 than the MAC address of this switch, which ends with 4580. So this switch is not the root bridge. The root bridge in the network is switch S3. We can also look down here at the switch ports, and we can see that switch port Fast Ethernet 3 is in forwarding mode, but switch port Fast Ethernet 4 is in blocking mode. So the spanning tree protocol has put switch port 4 into blocking mode so as to not have a switching loop in the network. Why did the spanning tree protocol choose to put switch port 4 into blocking mode versus switch port 3? Well, since both switch ports have the same cost value of 19 based on the speed of the link, it reverts to the priority number of the port, and you can see that port 4 has the higher priority number at 128.4 versus 128.3. So switch port 4 is the one that's put into blocking mode. Let's also look at the role and the status of the switch ports. Switch port 4, the status is blocking, and the role is alternate port. Switch port 3 is a root port, meaning it's the port closest to the root bridge, and its status is forwarding. Switch port 6, that connects to PCA, is a designated port, and it's also in forwarding mode. If we look at our graphic, we can see the roles for both switches. On switch S1, switch port 4 is an alternate role, switch port 3 the root role, and switch port 6 the designated role. The designated role and the root role both have a forwarding status, and the alternate role has a blocking status. If we look over at switch S3, which is the root bridge, you can see that all of its switch ports have the designated role, and they're all in a forwarding status. When we look at this graphic, you can see blocking is the status of switch port 4, and PCA can communicate with PCC over switch port 3 to switch port 3. Let's shut down switch port 3 on switch S1 and watch as switch port 4 goes from blocking to listening to learning and then to forwarding as the spanning tree protocol notices the change in the network and changes the blocking port from blocking to forwarding. I'll go back to my console connection, and before I shut down switch port 3, I'll put in a debug spanning -tree events to turn on event debugging. And now I'll go to global configuration mode, interface Fast Ethernet 0/3, and shut it down. We can see right away that a new root port has been established on port 4 with a cost of 19. So the spanning tree protocol has recognized that our forwarding port has gone down, and it has now made switch port 4 the new root port. Switch port 4 is listening, and you can see here there's been a topology change notice on switch port 4, and switch port 4 is now learning. You can see there FA 0/4 is learning, and now Fast Ethernet switch port 4 is now in forwarding mode. If I do a Control-C on my keyboard and go back to privileged user mode and do a show span command, you can see that switch port 4 is now changed from a blocking status to a forwarding status, and the role has changed from alternate to root. If I open up my command prompt for PCA and I ping 192.168 192.1.3, which is PCC, you can see that I can still communicate with PCC because the spanning tree protocol has enabled the alternate link in order to reach the destination. I'll reactivate switch port 3 by putting in a no shutdown command, and we can watch as the spanning tree protocol detects the change in the network and sets up switch port 3 as the new root port. You can see that switch port 4 has gone back to a blocking state. Switch port 3 is learning and now forwarding. I'll do a Control C on my keyboard and do a show span, and you can see that switch port 4 is back in blocking mode and switch port 3 has returned to its active forwarding state as the root port. Let's see what happens to the network and our connectivity to PCC if we turn off the spanning tree protocol completely. What I'll do is telnet over to S3, I'll go to global configuration mode, and then I'll type in no span, I'll press tab, no spanning dash tree VLAN 1, and that turns off the spanning tree protocol on switch S3. I'll Control C and then exit to go back to switch S1. So now I'm back in switch S1, and I'll do the same thing. I'll go to global configuration mode and type no spanning dash tree. Notice you can see here that I left on debug spanning tree events, and you can see here that we've received some information from the spanning tree protocol. Notice that VLAN 1, switch S1, we are now the spanning tree root. So we're already the root bridge because I turned off the spanning tree protocol on switch S3. Now I'm going to turn off the spanning tree protocol on switch S1 and we'll see what happens. So no spanning tree VLAN 1, and you're going to see that we all of a sudden have problems. Basically, we have a situation where switch ports 3 and 4 are flapping, and due to the loop in the network, switch S1 and switch S3 are getting confused as to which MAC addresses should be associated with which ports. I'll open my command prompt and attempt to ping host PCC at 192.168.1.3. You can see that the requests are timing out, and PCA is having a hard time communicating and receiving echo replies from PCC at 192.168.1.3. If I do an ARP-A and look at my ARP cache, you can see that I have resolved the IP address to MAC address for PCC at 192.168.1.3, but I've probably initiated a broadcast storm on the network in resolving this MAC address from this IP address. I'll try to ping once again, and you can see that PCA is unable to get a response from PCC due to the broadcast storm on the network. I've returned to the console connection. As you can see, there are so many debug and output messages being sent to the console that it makes it difficult to even put in a simple command. In order to get the switch back to its normal state and turn the spanning tree protocol back on, I'm going to need to remove the Ethernet cables from switch ports 3 and switch ports 4, and hopefully that will get the switch ports to shut down and stop the output messages. I can also choose to restart the switch if the configuration has not been saved, and then the switch will restart and return to the previous saved configuration. Okay, the switch ports have changed state to down because I've removed the Ethernet cables. I can now do a Control C and turn off the spanning tree event debugging. I'll put in the command no debug spanning dash tree events to turn off the event debugging. And then I'll go into global configuration mode and put in a spanning -tree VLAN 1 command to turn the spanning tree protocol back on. Now that I've done that, I can put the Ethernet cables back into the switch ports. You can see that the switch ports have changed state to up. And now what I'll need to do is switch my console connection over to S3 and do the same thing.